Welcome to the latest of the videos in the series brought to you by the volunteers of the IET in Surrey. And this time we're coming back to the idea of AI, a topic that's very much in the news at the moment. Last time, you may remember, we looked at how to detect deepfake images, and this time we're looking at how large language models such as ChatGPT can be used in everyday applications like helping with healthcare, detecting possible outcomes in healthcare, and also such problems that it may throw up, like people faking their essays and how to detect that. So we were very lucky to welcome Diptesh Kanojia from the University of Surrey, and he's doing research at the moment into large language models and NLP processing. And this is how we generate large language models and are able to input questions and get text answers coming out. Essays, of course, notwithstanding. So let's hear about what the challenges and opportunities are in NLP and ChatGPT from Dr. Diptesh Kanojia of the University of Surrey.
Engineering is the melting pot of innovation, where science, technology and design come together. Whether you think about the invention of the wheel or the first use of fire to change the property of materials, engineering has always been at the heart of mankind's development. From energy, transport, design and production, built environment, to IT and communications. Formed in 1871 and incorporated by Royal Charter in 1921, the IET is a world-leading professional organisation, sharing and advancing knowledge to promote science, engineering and technology across the world.
A very good evening, everyone. I'm Diptesh Kanojia, as Nigel has already introduced me. I am here as a lecturer at the Institute for People-Centered AI, and I have been doing natural language processing research for almost a decade now. Today, I'm going to talk about generative artificial intelligence and natural language processing and the people-centered perspective from which we do research here at the University of Surrey. I'm going to talk to you about generative artificial intelligence, introduce you to natural language processing, and then go straight to large language models, or what ChatGPT actually is. Then we'll talk a little bit about the evolution of language models which led to ChatGPT and a little bit beyond. But more importantly, what are the recent engineering advances in language processing which are making it possible for us to engineer solutions which are more efficient, more reliable, more trustworthy, and so on and so forth. We'll talk a little bit about the challenges and risks of deploying artificial intelligence models in the public domain, and then about the people-centered approach that we take here, and a small spotlight on the initiatives that we have here. Generative artificial intelligence is essentially deals with computational models which can either generate language or images or video or speech and so on and so forth. But the current advancements in artificial intelligence are driven by this NLP architecture that was proposed back in 2017, known as the Transformers architecture. And it's driving innovation in not just NLP, in computer vision and speech alike. But there's a commonality amongst all of these computational models, whether they come from computer vision, whether they come from natural language processing or speech recognition, and that is that any modality's input that you provide is supposed to be converted to mathematical representation depending on the context that you provide with the input, right? And essentially, this leads to the task of language modeling, which means building a computational model which has an idea or a worldview of different concepts that language can represent, and the most related concepts are clustered with each other within this computational model. So essentially, it has an idea of the context a word can be used in. How that happens, we will get to it, but before all of that, let's look at the main key goals of language processing. And at the very base of it, natural language processing tries to make sure that machines can make sense of human language, or quote unquote understand human language. But when that understanding has been achieved to a certain extent, natural language processing models or tasks essentially deal with analyzing human language or extracting information or retrieving information from some sort of database or from some sort of data set that you provided. Generating human language is another long-standing goal of natural language processing and a huge challenge. In today's day and age, yes, we see ChatGPT generate a lot of fluent text and other such language models generating a lot of fluent text. However, adequacy or accuracy of the text they generate is still very questionable. Language processing and computational linguistics are very much alike in terms of what they would like to achieve, but they fall at the confluence of linguistics and computer science. So if you look at the domains of computer science which deal with natural language processing, machine learning, probability theory, parsing, finite state machines, graphs and trees, and on the side of linguistics you have semantics, syntactics, morphology and lexicon. And depending on what you want the task to do, that task could either lead to an outcome which is more aligned to computational linguistics, or an outcome which is more aligned to natural language processing, having a more sort of a social impact, like the problem of machine translation, right? Like the problem of sentiment analysis for product reviews that you put up on e-commerce websites. How this all started was with J.R. Firth's paper, A Synopsis of Linguistic Theory from 30 to 1955. And there was a sentence which popularly says, "You shall know a word by the company it keeps." Given the examples, I'm sure you know what J.R. Firth was trying to explain using collocations here. But essentially what it meant was that the context of a word is important to decipher its meaning or sense. And it's this very grounded principle based on which generations of research in the problem of sense disambiguation in NLP or machine translation, or language modeling for that example, has been driven only because we realized that the context of a word is very important to decipher its meaning. But how do language models do it today? It's not just the context, the innovation, as I said, the transformer model. Let's not get into a lot of detail, but let's just try to understand how it generates language. And essentially that task that it trains itself to do is next word prediction. And this next word prediction is iterative. It depends on what tokens have previously occurred. So for example, if you say that I want to start a sentence, and I'm giving you an input where the input is robot must obey, and you are to generate the next word. Given the context and given the billions and millions of sentences that this model is trained on, it will probably throw the word orders, which essentially leads to the sentence saying robot must obey orders. However, reaching this stage, from a stage where we only knew that context is important, is not a very short journey. Language models since 1957 to 2024 have seen a lot of evolution, but the major leap in language modeling came with the proposal of self-attention in the encoder-decoder architecture that was proposed by this original paper titled "Attention is All You Need." And what self-attention does, it basically tells the language model while it's training itself to generate language or understand language, self-attention tells the model that these are the particular tokens which need to be given more attention to, or which are important to predict a particular word given the previous words. All of this innovation was also as much engineering, as much research, because the transformers architecture was proposed first. Then you have the OpenAI transformer, and the first language model which tried to do contextual language modeling called ELMO, and then you also have a ULM fit approach which came with a model which taught us how to transfer knowledge that is learned by a language model from that language model for a particular task. And once we had this language model called BERT in 2018, given all of these previous advancements, we could build encoders which could convert, given an input text or an input sequence of text, into mathematical representation or numbers. But what do we really do with these mathematical representations or these numbers? Essentially, if you pair an encoder and decoder, let's say, and train them on the task of machine translation, give it sufficient amount of samples which tell it that a sentence like I need some coffee needs to be translated to, in Hindi, mujhe kuch coffee chahiye, essentially meaning this very similar thing. If you train an encoder and decoder architecture, essentially you can, in theory, solve the problem of machine translation. How this architecture relates to what I said about the goals of natural language processing is when you are able to build a language model or understand human language, the encoder side of models can try to help you perform information extraction, information retrieval, textual analytics, and the analysis of sentiment, emotion, and so on and so forth. Many different tasks. However, the decoder side of the transformer architecture helps you generate language, which essentially means it can help you translate language, it can help you summarize a piece of text, or it can generate a dialogue given an input question or an input dialogue, right? But if the encoder and decoder, these are separate, how do you build them together, or how do you even understand human language, you may ask? Let's try to see what engineers the backbone of natural language processing. It's this task which is done in a semi-supervised manner. And semi-supervised machine learning essentially means that you have given the model a training objective where the model tries to train itself by predicting something. If it predicts wrongly, it changes its direction, it tries to go in a different direction and predict something else. And based on the loss value or the loss or the error amount of error that model sees during this prediction stage or during this pre-training stage, the model eventually learns what word or what token will appear in what context. And this novel pre-training objective is essentially a very simple task that we give to the language models. You have, let's say, millions of lines of text from Wikipedia or different books. You collect all of those millions of lines, you mask a certain percentage of words with this token mask, and essentially ask the language model to try and predict what's going to come in place of the mask. So let's take the example sentence. I love making slides at 11 p.m. in the blank. So given the context PM, the model should essentially say night. Why would I schedule a mask during a busy semester? The model might know that I'm talking about a talk or a task or some other activity that someone does during a busy semester. So essentially, if the model has sufficient amount of context, it's able to predict some words given, some blank masks given an empty token, and in the process it learns what context for each word or each token means. However, if the model learns all of this and understands context and can convert your given piece of text into some set of numbers, what do you really do with it? The task of fine-tuning, or as I said earlier, transfer learning, essentially allows you to take a pre-trained or a pre-built language model, and using that you can train a machine learning based classifier on top of it. Allow me to give you an example in a second. A classifier is essentially something that you can use eventually to say whether something is spam or not spam. positive or negative or neutral, joyful, rageful, sad, right? If you give it sufficient amount of examples that this piece of text belongs to the X category of class or label, and this piece of text belongs to the Y category of class or labels, given these examples, the model can become a classifier or a computational model, which given any new input can perform the classification task for you. The use of the clubbing of labeled data with these pre-trained language models led to a lot of improvement in performance of different NLP tasks that we do. For example, the task of entity recognition. Let's take an example of a research paper from the biomedical domain. It contains a lot of abbreviations and some long forms for those abbreviations. If you want to build a model which can extract all the relevant abbreviations and relevant long forms, you need to create a data set which has all of those things marked. And even if you don't have an example for every type of abbreviation, given the context of the paragraph which you provide as an input later, the model will try to understand where abbreviations lie, structurally speaking, or how long forms are connected to those abbreviations, and the model can extract this information for you. Let's look at the task of retrieval. So I'm sure all of you have used e-commerce websites, Amazon, Flipkart, or something else, and given a search query, for example, Galaxy S24, the language model or the computational model that you've trained behind, that is working behind an e-commerce website, will essentially try to reach products which are Galaxy 24 Ultra, Galaxy 24 Pro, or Galaxy 24 some other variant. But its objective is not to reach products like Galaxy S24 cases or Galaxy S24 screen covers. Depending on what kind of relevant data this e-commerce engine is trained on, built on a language model, you can essentially retrieve relevant products. If you look at the task of classification, there was a lot of improvement in the detection of spam, in the identification of sentiment, emotion, sarcasm, aggression, toxicity, and all of this in the domain of social NLP, which we also do here at the University of Surrey. I think I've already given you an example of classification, so I'll probably skip these slides. This is just an example of how a data set of your emails can probably be labeled and be used to train a classifier on top of a language model. If you look at the task of evaluation, language models are used here too. So for example, if you have a source sentence which says, I need some coffee, and the machine translation output for that sentence in Hindi says, Mujhe kuch coffee chahiye, where as a human annotator, I know that kuch is probably not supposed to be there. It's translating to some, but it doesn't really sound fluent in Hindi. As a human annotator, I know this is a fluency error, and let's say I give it a quality score 65. If I find enough of such examples or annotate enough of such examples, language models could also be trained to provide a quality evaluation or a quality estimation score for how well the translation has been done. And if you don't believe me that in today's day and age, machine translation can make such a trivial error, this is a screenshot from last night. This is Google Translate, and it's definitely a fluency error. But if you would visualize the evolution of language modeling from 2017 to 2024, we have had hundreds of new language models. ChatGPT is probably one of the most popular ones, but there are a lot of publicly available language models which come in different sizes, different flavors. For example, the smallest models like the BERT model, I probably know them to be around 100 million parameters in size. When you train a model on large amounts of data, the model essentially stores a lot of numbers in the form of a matrix which needs to be stored on the disk. And if the BERT model with around 100 million parameters was costing 2 to 3 GBs of disk space back then, imagine what amount of disk space computational models worth 170 plus billion parameters would take. So as this leap in language modeling or leap in the evolution of whole genre of NLP models arrived, we are seeing a lot of problems in terms of storing these models or using these models for different NLP tasks because they are growing in size on a daily basis. Some of these models are catered to a particular domain. For example, if they are only trained on biomedical data, they can perform biomedical tasks very well, like biomedical information extraction, as I talked about, abbreviation and long form detection, or for that matter, clinical report generation if you provide it with thousands and thousands of clinical reports perhaps. Essentially, a language model has a set vocabulary, and if you train a language model on a particular domain of data, then it will acquire that vocabulary and hopefully generate it slightly more accurately. These models can come as language specific models as well, and Airavata is one of our own efforts which we launched very recently. It's a large language model for the Hindi language, and these models can be task oriented as well. Some models can simply be used as a chat assistant. Some models are geared towards a particular task like translation. Some models are geared towards a particular task like e-commerce product query relevance, right? But language generation in NLP is not new. It's not like ChatGPT arrived and we were all suddenly wondering what has happened. Language generation has been in NLP for a while, although it was not as fluent, I fully agree. But we have been researching the problems of machine translation, text summarization, and dialogue generation, all in the domain of language generation for a long time. And with the arrival of recent models like GPT-3, ChatGPT, synthetic data generation has sort of become a possibility, which essentially means if you want to train a model to produce counter narratives of hate speech, you can essentially ask it to generate that data. So if you train it on some examples of counter narratives given a piece of text from social media which we know to be hateful, if you give it some counter narratives for that piece of text and train it on generating those counter narratives, models will be able to generate more and more synthetic data for you for that particular domain, for that particular task or problem. Similarly, data labeling is something models are now being used for. So further training a model requires more labeled data, but data, when it's labeled by humans, it's a cost and time inefficient task because it takes a lot of time and a lot of money to acquire clean and filtered labeled data. So models are now being used to generate labels for data instances. So you crawl a lot of social media data and you can essentially ask a model whether this is positive in sentiment or negative in sentiment, or whether this is sarcastic or hateful, and so on and so forth. Further, models can also be used to generate creative text like poetry. Before ChatGPT came in, what really led to the whole revolution of publicly available or open large language models was this model called InstructGPT, also released by OpenAI. So if you look at the prompt, I apologize if the font is too small, but it says explain the moon landing to a 6-year-old in few sentences. And the initial GPT-3 model, if you look at the output, it just goes to say explain the theory of gravity to a 6-year-old, then explain the theory of relativity to a 6-year-old in a few sentences, then explain the Big Bang theory to a 6-year-old, and then explain evolution to a 6-year-old. Whereas if you provide sufficient data on how to explain a particular concept to a 6-year-old, model will start to learn. And with such instructions, if you tune the model, you will have something like InstructGPT, which says people went to the moon, they took pictures of what they saw and sent them back to the earth so we could all see them. Instead of providing a very generic non-meaningful or non-coherent output. Now we have something which can actually be used to explain a particular concept to a 6-year-old. What led to the whole furor is the release of ChatGPT in November 2022, and its penetration amongst researchers and laymen has essentially shown us that a lot of different tasks can be modeled for a language model to perform, and language models can act as your chat assistants. Language models can act as your computational models which deal with data labeling. They can translate for you, summarize or paraphrase, or given your chain of thought, they can generate your reports or literature reviews or surveys, which I hope none of you do. You can see some students in the audience. GPT 3.5 Turbo was essentially just an instruction tuned model built on top of GPT 3.5, which led to ChatGPT. But these instructions were based on a lot of different NLP tasks. Probably OpenAI doesn't tell us what they do. They're not very open about it, but I am assuming there were a lot of instructions and a lot of what we know as feedback loop based instructions, which told ChatGPT or informed or trained ChatGPT to essentially produce output which was aligned with quote unquote human values. So for example, ChatGPT outputs a toxic sentence or a few aggressive sentences. If you annotate them with the help of humans, remove that toxicity or bias or misinformation within the output, then using both of these examples, you can align ChatGPT or other such large language models to produce non-biased, non-toxic, and more truthful information. Essentially, this is what they call language model alignment. You just have to provide enough instances that given this question, do not say this, say that instead. And this is how LLM alignment works. And these engineering challenges in scaling that OpenAI initially faced when they released ChatGPT led to a lot of times when the website was down, but their collaboration with Microsoft led to the deployment of what we know as co-pilots today. If you open your Edge browser or if you download the Android app Bing on your phone, you essentially get an instance of a GPT-like model right in your hands, and you can talk to it, you can ask it questions. Given internet connection, I guess, you can ask it to search for things for you, right? Search for things with a context. And this is also what has raised a question that traditional information retrieval, which was based on a lot of indexed documents from the web, is it going to change? Are we going to see a new paradigm of information retrieval where language models will answer your questions instead of search queries searching through a large database, which was the previous paradigm? But all of this accessibility and this impact on non-experts has also led to a lot of misinformation generation, or a lot of misuse of AI, which is really concerning. But publicly available large language models, apart from even ChatGPT, they grow in size, they grow in number on a daily basis. In academia, given the restricted infrastructure, how do we adapt to this? Because there's a lot of synergy between engineering and research now, you see approaches like low rank adaptation, parameter efficient fine tuning, fusion approaches, and retrieval augmented generation. I'm going to try and explain these concepts with examples. So if you do not have a large enough infrastructure to train a very large variant of such a model, language models are essentially matrices. If you downgrade your matrix, the hypothesis for this research is essentially that a lower rank matrix or a certain part of the matrix will contain sufficient information for doing a task. And given this sufficient information or a certain restricted or significantly lower number of parameters you can extract from that matrix or that computational model, and you can train what we call a smaller language model adapter. And that adapter can be trained or tuned for any particular task. You can train it for translation, you could train it for quality estimation, extraction of information, and so on and so forth. And recent studies have also reported, recent papers have also reported that these adapters are up to 95% efficient compared to the original model sizes, which are almost 10 times larger than these smaller adapters. Further, if you deal with smaller variants of language models, and if you do not have the infrastructure to deal with the larger variants of language models, you can employ this very recent technique, which is called SPIN, which is built on a self-play mechanism. Essentially, it generates its own training data. As I discussed LLM alignment a few minutes ago, it generates training data and aligns itself, discerning its own output from a human annotated output or a non-biased output or a more accurate output for that matter. And using this strategy, it learns to generate more accurate and better content. Further, another engineering innovation which helps us produce better performing language models, which is fusion of language models. And in the olden days, or conventional fusion approaches essentially deal with what we know as ensembling of models in machine learning. You can club multiple models together. There are different ways to do this. In one of the ways, you can just take the same output from multiple different models and aggregate it based on some equation or based on some score, which essentially says that this model's output is perhaps to be given more weightage, or Y model's output is perhaps to be given more weightage, right? So this ensembling can also be done at the level of model weights. As I've been talking about these matrices which are inside of a computational model, you can directly infer from these matrices the output and then try to use some model operation or vector operation to try and produce a desired output or a more accurate output. Fuse LLM as a technique, however, can source multiple different language models and use their probability matrices to fuse a single small matrix, and this innovation can essentially allow you to produce an output which can contain pre-trained language model data from either different domains or different languages, or let's say the model catered to different, each of these three models catered to different tasks, but now your combined model or fused model caters to all of the tasks, right? Language models with these engineering innovations, including retrieval-augmented generation, which I will try to explain here, are applied in various domains. And retrieval-augmented generation essentially clubs the generation of text from a language model along with a structured data source. Let's say you have your schedule as a table somewhere lying as a data set where all of your appointments, all of your the whole of your diary, your calendar is present as a structured database somewhere. If you club this with a language model which can work as a chat assistant, essentially the language model can tell someone that no, XYZ person is busy at 7 p.m. on Monday, because it can get that information from the structured data source. In the healthcare setting, however, let's talk about an example where a lot of pre-operative assessments have been done over the years, but the doctors at the hospital now want to find some particular insights about a particular operation perhaps, or a particular patient. If that structured data in the hospital is not anonymized, then you can connect a language model to it and essentially ask questions about the patient. or a particular case, or try to derive insights from multiple cases which happened over a period of years. Structured data, when connected with a large language model, provides that accuracy that large language models essentially lack, and try to generate text without having a clue of what they are talking about. And similarly, in this particular case study report, in Singapore, they used large language models in the retrieval-augmented generation setting and looked at a lot of pre-operative assessments, and eventually the results say that combining ChatGPT with their internal data gives them output which is comparable to what humans could do given a set of questions. Retrieval augmentation along with LLMs has essentially led to a revolution in the sense that a lot of solutions are being engineered, whether it's the healthcare domain or the e-commerce domain, or whether it's the finance domain, for example, because in the finance domain, of course, you deal with a lot of numbers and any inaccuracy can cost you a lot. In the e-com, let's not get into the technicalities of the figure, but in the e-commerce domain, language models are applied as dual encoder architectures where, I mean, this is one of the architectures. Of course, there can be many different permutations of how you use a language model to retrieve a few products on an e-commerce website. But given a query and a set of products which you need to rank, you can use either a bi-encoder setting or a cross-encoder setting. In the cross-encoder setting, essentially you look at a lot of products and prune your search space, and given the query, you say that these X and Y products should go ahead to the bi-encoder. However, this Z product is not really relevant, and I'm going to prune it off here itself. So essentially the bi-encoder later ranks and shows you which products are more relevant on top of your search engine page. There are different applications for these large language models, and they are being applied to a lot of different domains, a lot of different sectors already. Startups are cropping up which are promising you solutions for mental health problems, or becoming a mental health first aider, where a large language model would be used in an online setting to try and help someone who may be about to commit suicide. Such solutions are very risky, and there are a lot of challenges in dealing with large language models because of the kind of accuracy or the kind of content they generate. One of the challenges for academia, of course, is coping with AI generated text. Students using such text in reports and research papers is not something any of us wants, but there are methods to try and detect this. Authorship attribution is a field in natural language processing where we try to look at what computational model may have generated this text, and authorship attribution datasets contain a lot of examples from models like GPT-2, GPT-3 and many other such language models, and they can tell you whether this text has been generated by a GPT-like model or whether this text has been generated by a BERT-like model. Oh, sorry, not really generated by BERT-like model, but a BERT clubbed with a decoder-like model, essentially. I would like to give some examples of the misuse of AI given the newspaper headings we have been recently seeing. So if you look at this one, paper retracted when authors caught using ChatGPT to write it, and they were caught because the ChatGPT query to regenerate response had been copy pasted in the paper. Yes, that's not a mistake you should make if you are copying text from ChatGPT output to write your research papers. Given the election year, there's a lot of risk of misinformation spreading amongst the general public, and very recent headline, tech giants have come together to try and see if they can combat misuse of AI and misinformation this election year. Another headline, is this an appropriate use of AI or not? Teachers say classrooms are now AI testing labs, where all apparently students do is submit the work that is generated by language models. The risks in using a generative AI model stem because of many different things, but primarily it's because of the kind of data these models are trained on. Because to be able to curate digital data or data written in a particular language, billions and billions of lines, to be able to train a language model using that data requires a lot of infrastructure, requires a lot of sources where you can curate data from, and unfortunately a lot of clean and filtered and non-toxic digital data is unavailable. Hence what a lot of tech giants who have just vowed to fight misinformation, what they resort to is essentially scouring the internet for Reddit posts, social media data, anything and everything that they can get their hands on, and essentially use that data to train a large language model. And training at this scale requires a large amount of data, but using anything from the web, whether it's GitHub code or a Reddit post or a Wikipedia article, essentially leads to a language model which is able to generate toxic output, which knows toxicity, which knows hate speech. Textual deepfakes and visual deepfakes have also become very common nowadays. I'm sure you must have heard something in the news about misinformation or disinformation, or somebody spread a rumor about something. They produced an image from ChatGPT which was looking very official, very much like a government certificate or some sort of government policy paper, and they released it on the internet. Therefore, safety and content moderation from what is generated from these language models it becomes essential. Therefore, safety evaluation of these language models, in the sense that how much do they understand toxicity, or how much can they detect hate speech, or how aggressive their speech is. All of these evaluations or tests using benchmark datasets should be carried out when a language model is being released in the public. LLM alignment should be done to align the LLM with some human values, and at least not allow it to produce toxic or misinformed or non-truthful content. In light of that, one of my friends was having this chat with ChatGPT where they asked it, what is 44 in Hindi? And ChatGPT said it's 24, which we know is 24. So my friend ended up asking, then what is 24 in Hindi? And ChatGPT says the number 24 in Hindi is 24. So my friend asked, so both 44 and 24 are apparently the same in Hindi language. We don't know numbers. And then ChatGPT corrected itself. And this is very recent. This is a model which has been trained on billions of lines of corpus. It knows how to translate English to Hindi very, very well in some of the cases that I have used it for. It knows how to translate from English to many other languages, but it does not know the difference between 24 and 44. That's what is problematic with these language models. They can do the most complex of things, and at the same time, they cannot do the simplest of things. And because of the black box nature of neural networks on which these models are trained, their processes are not interpretable. Essentially, what goes into a language model or a neural network is something you can see and interpret. What comes out, you can see and interpret. What happens within what we call hidden layers, and that's not something that is very interpretable. And due to this very nature, due to this very nature of neural networks, there is a lot of research on a particular section in AI called as explainability, where the neural networks are supposed to not just provide an outcome or predict an outcome for a given situation or provide an answer for a question, but also explain their answer. or explain why a neural network said that this man should not be given parole or this man should not be given a particular kind of medical treatment. If a language model is being allowed to make such decisions which can harm someone's life or change the trajectory of someone's life altogether, then these models need to explain their decisions or explain the outcomes. Pertinent example from a very, very well known, publicly available large language model, Llama 2. It's been released by Meta, and the paper itself shows you this graph, which shows you where or how much toxicity is present in its pre-training data. And if you see towards 1.0, there are a lot of instances which contain toxicity. Actually, if you start very much from 0.1, even if something is 10% toxic, it's toxic, right? At least I seem to think so. So right from here to here, a lot of data is toxic in such language models. And what their paper says is, to allow for better downstream generalization, we choose not to scrub toxic data from pre-training. No filtration, use of toxic data as it is. So what do we do here at people-centered AI? Why am I talking about the challenges, the risks of artificial intelligence or its use? Here at people-centered AI, we prioritize low resource and endangered languages where research has not been done in a significant amount for a particular language. We try and find efficient and scalable approaches to language modeling, and we try and evaluate large language models for bias, toxicity, misinformation. Further, we also deal with the detection of aggression and offensive language on social media, including a particular data set that we released which discussed political aggression. What do we do in terms of efficient information extraction? Let's not look at the numbers right now. With this particular paper, what the results are trying to show is that you can build models which are not based on the transformer architecture, which are cost efficient in terms of training and can perform almost as good as the transformer models. In terms of quality estimation, let's not go to the results table. I will actually in a second, but what we are doing is training language family dependent quality estimation models, which means that if you only need to provide quality estimation for a particular family of languages, only train the model on that data. You don't need to train bigger models necessarily for everything. You can deal with a sufficient amount of data, you can deal with an efficient approach to training your model and essentially get something. So if you look at the correlation score, Spearman correlation score particularly, is my mouse visible? No. Is it visible now? So yeah, if you look at the Spearman correlation score for the English Gujarati language pair, this number that we achieved here, 0.713, is actually only 0.001 behind the best performing ensemble of models at a challenge that was proposed online. We participated in the challenge, and a single model using our approach generated a correlation score of 0.713, whereas what the winning team had used was 12 models, at least 3 times in size of our original model, and using that brute force they reached 0.714. It's not necessary to go large and go big every time. In terms of efficient retrieval and ranking, we are working with eBay, and we have recently proposed a more efficient technique to language modeling because the search engine they use needs to produce results quickly, needs to produce results which are more relevant to the users or which the user really intended to see. We have proposed the use of contextual character level language models with the attention layers, which is a modification that we propose with this BiLSTM architecture, where our approach will hopefully help eBay deploy language models behind their search engine, which are smaller in size and which can still do efficient retrieval for them. We also prioritize our investigations in toxicity and truthfulness here at Surrey, and therefore we try to always use non-toxic data for pre-training. If we are doing that, we try to make sure that our models only generate verifiable and factual information based on trustworthiness in AI, which is a challenge identified, a grand challenge identified by the Surrey Institute for People-Centered AI. And we try to also align models which do not generate a toxic output. And in this interest, I contributed to the bias, toxicity, and misinformation evaluation for this particular Hindi instruction-tuned large language model, which has very recently been released. Further, we are also trying to work with the Southwest London Elective Orthopedic Centre. With the help of large language models, we are trying to derive insights towards personalized healthcare. We are trying to derive insights from various data sources that they have from the NHS, and trying to look at preoperative assessments, the clinical reports they have, anonymized patient data, and then see if we can personalize healthcare for different demographies that come to the hospital for orthopedic care. So, all in all, generative AI, it's as much engineering as it is research, and recent advancements can help you engineer solutions to problems across various sectors and across various domains. But generative AI and the growth of large language models, this poses a new challenge and new risks to education, to the social fabric, to mental health, and we need a people-centered approach to language modeling. So we are trying to do our part here. And that should be all from my side. Thanks. Thank you so much, everyone.
Yes, thank you very much for the talk. One of the things you talked about is eliminating toxicity.
Right.
And is this not a very subjective view? There are certain phrases that somebody might think is totally innocent. The one that occurs to me straight away is the phrase, from the river to the sea. Now, I think some people who say that in public can now get arrested. I would never have thought a few months ago there was anything wrong with that. So how do you remove toxicity, identify it and remove it?
Natural language processing nowadays is looking at perspectivism when it comes to data labeling. What you asked in terms of what can or what cannot be said, and the subjectivity of the labels or the data that we use. If you employ annotators from different demographies, if you employ annotators from different countries, different backgrounds, you will find different perspectives on data annotation, and things are subjective. I fully agree. For example, the translation output that I showed you, that to many might have been absolutely fluent and okay, but if you show that to a linguist, they will, which my wife here in the audience also checked. They will tell you there's a fluency problem. So subjectivity is, and ambiguity is a part and parcel of language. What you can and cannot do is, at max, give your language model sufficient training examples or sufficient labeled data which is aligned with what you think is toxic, what you think is hateful versus what you think is non-toxic and non-hateful. Does that answer your question?
Firstly, thank you for the insightful talk.
Thank you.
I want to ask, so how do we find the standard if a small language model would be more efficient than a large language model modified in a specific niche? How do we find which is more optimal?
There are benchmark data sets available in language processing research. Whatever task you want to watch your model perform better at, you use the benchmark data sets for testing the model performance before and after fine-tuning, and then you realize how much gains you have gotten after you fine-tune, essentially.
So for now, it's just testing.
Essentially, you test on different data sets. If you want to look at your model's performance for a particular task, that task should have a data set. And if it does not have a data set, then you ask your model to do that particular task. Let's say it's translation over a number of samples, and you employ a human to rate those translations, which is cost inefficient, I guess. So it's better to look for existing data sets initially when you're doing research and trying to look at how well language models can perform for a particular task.
Thank you very much.
Thanks.
It's on. Hello there. The gentleman behind me struck a thought in my mind, which may be, I hope, relevant. But if I understand things correctly, you have human input to help train a large language model.
Yes.
And after a while, the large language model can create hypotheses on its own, and those are approved or trained or tuned by a human. Which makes perfect sense to me, except when we then talk about toxicity between languages and religion and rate and all the other complex things that humans can do, how do you ensure that the human input is as unbiased as it can be? What do you do to ensure that the humans interfacing with the large language model are actually integral in themselves?
We try to deal with it with the help of annotation guidelines. As clear as you can be in your annotation guidelines when you are asking humans to provide you labels on a certain number of data instances, you have to let them know that our annotation is supposed to be grounded on a certain principles, and these principles mean that this particular example, you have to label it as hate. This particular example, you have to label it as non-hateful. So, yeah, we provide annotation guidelines as these. You can ask me in the class.
Some authors have described what appears to be hallucination-like phenomena as output of language models. One thing I saw cited was somebody asked a language model to produce a discussion of the role of bears in space exploration, and it produced a very fluent piece of text about how bears had contributed to space exploration. As far as I know, there haven't been any bears in space. Can you offer any explanation of how that sort of thing might occur?
Why hallucinations occur is not known to the community, as I say, the black box nature of neural networks. But to counter hallucinations, LLM alignment has been very helpful. If you take the hallucinated output versus a human annotated output, which says that, which answers the question in very short words or something, then you essentially can align your LLM to not produce hallucinations.
So you'd hope that those would be eliminated by retraining effectively?
Exactly.
Okay,
Yes.
thank you.
Yeah.
Can go.
You mentioned in the discussion about training language models. Sorry, you mentioned in the discussion about training language models about the ability of language models today reaching the same competence as surgeons in preoperative surgery. How can you tell when the language model is smarter?
That's where the game is rigged, I would say. They take a particular test set, they ask a human to perform annotations on the test set, while a language model also does the same task. If the language model seems to beat one human at that particular task, it becomes newspaper headlines. In terms of translation, because I do a lot of research in that area, what I can say is I have seen papers and studies and newspaper articles even which say that machine translation has reached human parity, which is, to my mind, that's very boggling. What about metaphors? What about idioms? Idiomatic translation is an absolute failure. So reaching human parity is, I think, and what you say about beating surgeons and lawyers at their own game, that's happening over specific use cases. What context and what education a lawyer or a surgeon has acquired, you cannot hope a language model can do all of those things in the same manner as the human can. This is just about a particular thing. Yeah.
So one of the areas that generative AI in NLP is revolutionizing is search. A lot of the ways where such models are implemented are usually domain specific. There's a known set of knowledge that they need to convey, and they can be fact checked. But specifically in the area of search, where you're indexing unlimited information, one of the challenges that a lot of companies are solving, whether it's using Bard or whether it's using a Copilot, is correctness of the responses. You can't have a definite test set to check that all your search queries will be correct. How does that challenge tackled? I have seen Perplexity do it in one way, where they're giving a best case guarantee of a correct information. But how is that going to go forward? Because right now it still comes across as an experiment.
Fair. That's a fair question, but e-commerce industries have their own internal data sets, and based on what kind of approach they would like to use, there's a lot of internal testing which goes on, and it's not just about searching for a product. This becomes more of a ranking problem for them. So essentially, given a search query, model is supposed to rank the most relevant products on top, and such examples are provided in the data sets that these people work on. So eBay has a lot of different such data sets internally, where for a particular query, a top ranked product is provided, or a rank 4 product, or a rank 3 product, and so on and so forth. So for the same query, if you have a certain number of examples which say that this is very relevant for the query, while this is not very relevant for the query, again, it's simple machine learning, and they do ranking.
Thank you very much. It was very enjoyable. There's been a lot of anxiety in various areas of the different workforces about AI replacing jobs. What's your sort of take on that? Do you see it as a threat or more of an opportunity for people to be doing different, more interesting things?
I'm not sure if I am if I can comment on that, but in terms of what human beings can do, a particular job, for example, let's say coding, it's writing a programming language that has a lot of structure built within. Such tasks maybe the language models can do on their own, and maybe they will replace some developers at the entry level, but then we will require people to build and innovate for such language models, right? I am not sure if language models and AI models are going to take away a lot of jobs. I don't think I should comment, but there are of course a lot of things that human beings do at jobs which are way beyond what language models can understand or comprehend or even hope to do. So I'm not sure if that's really the case. I think it's just maybe the hype. Yeah.
Should we go for the last two? Yeah, I'll do one here. Yep.
Referring to an earlier question in your answer and the quest for human parity, presumably that quest is infinite.
That's true. And
could you see a situation whereby, because of that infinite condition, that a common language may evolve? And would our literature colleagues be ruining the day?
In terms of a common language evolving out of what we do or what we say and what the language models say, that's definitely going to happen at some point, because right now you see a lot of websites where the content is automatically generated by ChatGPT, and it's just barely been a year and a half since that model was released to the public. In terms of what we speak, how we speak, social media already changes how we behave, right? So if language model based content is out on the web, that may also happen. But I don't think I should comment on whether our literature colleagues will rule the day. But language models can definitely generate creative text, but I don't think they can be creative in a very meta sense, right? Implicit meanings of words, what wordplay is, what metaphor is, what idiomatic senses are. That's something that's still troublesome for language models, and I think our colleagues in literature have a very good grasp on these concepts.
There's been talk in the papers about children using AI to generate answers to their questions, etc. How do you actually detect that AI is being used to answer something rather than the child himself or herself actually responding with the information they know?
By using the same approach as we use for spam classification. We train computational models which have an idea of the language that is generated by GPT-2, GPT-3, and many other such generative models. And these text attribution models or authorship attribution models can essentially look at a piece of text and tell you if it's been generated by a particular language model or not. There are approaches to deal with this, yes. Although those approaches are not very accurate, I would not blame a student given authorship attribution model has told me that this is plagiarized. I would still manually look into it.
Would you join with me in thanking Diptesh for an excellent presentation?
Thank you for the opportunity, Nigel and Professor Taylor.